Hello guys, thanks for watching my video. So this is my presentation for the Scientific Computation for Social Sciences class. And what I decided to do my project on was NetworkX, which is a library to use on Python to do network analysis. So the question then becomes, why networks? And I think we give a lot of importance to networks nowadays, in part because of like the appearance of social networks on the internet, of stuff like Facebook and Twitter, and the amount of data that we can gather from studying it, or maybe even just from the data from the internet, which is, it is literally a network. However, we sometimes forget that there are, or we don't think that, social networks are way older than that. Social networks is how we interact with each other, and we can probably think of a network solution or a network angle to a lot of the um, research that we think of or do on social sciences, right? Um, so networks is how information gets spread. It's how we can see who is important in a group of people, who connects who, and it's for example, in my case of behavior, you can think of how it affects a lot of different uh, a lot of different behaviors, from communicating with other people and discussing opinions on politics and who to vote for, who to support, to stuff like deciding or not, or depending on who you're friends with, on who you interact with, on how to protest, on to decide to join a protest, or even some sort of armed rebellion. So I think it's an important component to consider when thinking of research, even beyond the type of the stuff that computational computational revolution of sorts that we live in has given us information on. Like, even beyond that, it's important to think on this, or consider this element. So what I will do is basically show you some of the things that you can do, like very basic things that you can do on NetworkX, and measurements that you can get out of it. So I think that the very so here's like spider visual console, like it's the right name for it. So I'm going to show you the code and some of the results of what I'm going to be doing. I think like the most important thing, or one of the best ways to begin with this, is to think of what is a graph, a node, and an edge. So I'm going to start by showing you. I'm going to create a graph, which is this part of the code, and then I'm going to add different nodes and edges to it. And a second, I'll say what that is, and then I'm going to make here at the end a visual representation of it, right? So I run this. Sorry. I have to start by importing the library, of course. So that's a problem that you might run into when using Python. Always remember to import libraries. Then you do this. So a graph is a visual representation of a network, and then the different elements of the network are the nodes, which are the circles here, which are the elements of it that are connected to one each other. They can be people, but they can be other type of things as well. But they are the elements that get connected, and then the edges are these different connections. So like we have like node J, and it's connected to node H by this edge, and then it's connected to node I by this edge, and H and I are connected by this edge. So this is an undirected network. So you have like the edges connecting on both directions, but you can also have directed graphs. So the graph is, as I said, the representation of the network. By using this different code, digraph, you can get a directed graph. So in this case, you can see that there is a direction. So node A connects towards node C by this direction, but it doesn't work the other way, right? So this is an important difference. So this graph is more like Facebook, when you have friends, right? Whereas this one is more like Twitter, where I can follow someone, but they don't necessarily follow me back. So to get just, like the metaphors with social networks going. So there are different things that you can do with graphs. You can add different attributes to it. So this is an example of how you can do that. Sorry. You can add a weight and a type of relation. So this is another graph that is pretty much the same as the other one. The graph will fit itself almost randomly. It doesn't really have like a logic as to why A is here in this case and here in the other case. But the important thing here is that maybe the relationships are different. Maybe some relationships are more important. So that's why I'm saying that weight 6 here, but weight 8 for this specific edge, right? Like the relationships can be more important, and then you have different types of relationships. Like maybe it's someone that you know from family, maybe it's someone that you know from work, and then you can add this information, and then you can sorry, it's really even live coding like this is terrible. And then you can get this information out by using this edges data equals true. Like it will tell you all the different types of parameters, not red parameters, more like information that you've included. You can do the same for nodes, so you can add information on the specific node. So say like a role, that's how it's used. The code is here, but I'm not gonna run it because it's pretty much works the same. But then of course the part that is important and interesting about network is like the connections between each other. So you can get different measurements of connectivity for each node. So probably the most important, or one of the most important concepts to start or to begin with, is this idea of degree. So I'm going to be showing these with this graph, so I'm going to keep it here. So like the degree is the number of connections that a node has. So for example, this J here has a degree of 3 because it's connected to node H, node G, and node I. So that's the most basic one that you can get it very easily. Just look at the graph, right? But you can also get a local clustering coefficient, which that is the proportion of connections that a node has that are connected amongst themselves. So for example, let's focus on A, right? Here's node A. When you get this code for local clustering coefficient, you'll get a 1, right? Because A is connected to node B, to node C, and node F. But B is connected to C, and B is connected to F, and C is connected to F. So all the nodes that are connected to A are also connected among themselves. So you get you get the maximum local clustering coefficient. And then based on this, you can get different measurements of global clustering coefficients. So and this is sometimes defined as like the tendency for edges to form triangles, right? So they're clustering. We all know what this is. They're like grouped together, right? So you can get an average of all the local clustering coefficients, which is done with this code. So for this specific graph, it's a 0.62. But you can also look at the proportion of like open triads, which is basically triangles that are not formed that are missing an edge. So I don't think I have any example here. Maybe like yeah. So like this is an example just for you to get an idea. Like this is an open triad in the sense that A is connected to C and C is connected to D, but there's no connection to D and A. So like the idea is to look at the proportion of these sort of like triangles that are missing one side and see when they will become, or whether they can become a proper triangle. So then you can get also for the first graph G1, you get the transitivity measurement, which is below the average clustering coefficient. And then you can also look at the distance between nodes. So the distance is the shortest path between two nodes. So for example, for G1, once again, let's look at node I and node B. You can get the shortest path, which is from I to F and F to B, which is what it tells you here, I to F and F to B. And then it can give you the length of this shortest path, which is what I'm going to give you here, which is 2, as we can probably tell from just looking at it, but it gives you 2. But of course, this is much more impressive when you have a network with thousands of nodes, right? You can get this information from one node to all the other nodes in the network, in the graph, by using that code. And then you can get you can represent these as a tree. So this is just like a way of getting these into more visual forms. You can run this code. And then, well, this is an interesting way of visualizing it. But basically, it tells you, like, for example, in this case, from A you can go directly to F. So the tree is represented that A can go directly to F. But say if you want to go from A to H, so from A to H, and it would be from A to F, F to I, and I to H, for example. So it will be from, oh well, it went to a completely different one, ACE. From A to C, C to E, E to H. So A to C, C to E, E28. So it's just a way of representing. Of course, if there are two paths that are exactly the same, this tree is going to give you one of them, not both of them. But it's like a way of visualizing it. And then you can get an average short span length for the entire network, for the entire graph, right? Which in this case is 1.64. And there are other types of measuring or looking at distance. So an important one is eccentricity. So the eccentricity in the network is the largest distance between one node and another node. So you will get one for each of the nodes. So the largest distance between A and another node is 3. The largest distance between B and another node is 3. But say like the largest distance between B and another node is 2, right? So the eccentricity will be a measurement for each of the nodes in the network. And then a diameter is basically the maximum eccentricity inside the network. So in this case, it's going to be 3, as it shows here. And the opposite is the radius, which is the minimum eccentricity. So obviously the names sound kind of familiar for geometry, right? Like in the case of a circle, right? It's like that is the way that I remember. Like in the circle, diameter is twice the radius. So one is for the biggest one, the other one for the smaller one. And the nodes that are that have whose eccentricity equals the diameter are going to be in the periphery of the network, right? They are the ones to be the ones on the most outside. So in this case, once again, we're looking at this graph. Those that have an eccentricity of 3, which equals the diameter, it's the largest eccentricity, would be on the periphery, and it's A, B, C, H, and J, and then the other ones would be at the center, would be the opposite of the periphery, those whose eccentricity equals the radius, and is F, E, D, G, and I. So then I'm gonna just mention briefly that there's a measure, let's say like a characteristic of connectedness, which means that for every pair of node you can get from one to the other. So I'm gonna make a graph that is not connected, so you can look at the difference. This is very similar to the first graph, to this graph that we're mostly looking at, but in this one, in this case, it's not connected. So it looks like a little bit like the graphs look small, but basically the idea here is that you have the same nodes and basically the same edges, except I cut away one part from the other. So this is a non-connected graph. So you can use this code to check whether a graph is connected or not. So for the case of this one graph, when I wrote this code here, it tells that it's connected. But if I do the same for this graph, it will tell you that it's not connected. So it's indicating false here. You can do the same, you can check the same for directed graphs, but in this case, there's two types of measurements. There's a strongly connected and weakly connected. So once again, thinking of this connected graph that we already saw, G2, it is strongly connected if for every node, you can arrive at another node by respecting the direction of the edges, and in this case it's going to be false because, for example, you cannot get to A from C. You can move from A to C, but C will never be capable of going back to A. And it's weakly connected if you just ignore the directions, treat it as an undirected graph, and you can get from any node to any node, in which case it's going to be true that they are connected. So that's a lot of measurements or things that you can look at the graph in general, but also to particular nodes. But sometimes what's important is what we are interested in, especially when we're looking at networks, is not so much, like the characteristics of every single node, but rather which are the important ones. Who is influential in this network? Who is spreading the information? Who is convincing others to do things? Which are the central parts of it. So for looking at this exactly, we can look at the centrality measures. Which will be dependent on how you define importance. So most of this I will be using the G1 graphic, right? This one. So one of the ones that we can look at is called degree centrality, which says that the nodes that are important and those that have many connections. So it moves from 0 to 1. 1 is the most connected. So what you do is that you use this nx.degree centrality, and then you use the name of the graph. And that doesn't give you anything because to get the degree centrality, it will be a measure of each node. So, but then you can use let's call it descent that we just defined to get the degree centrality for a specific node. So for this, for example, in this case B, you run it and then you get a degree centrality for B, which is 0.44, right? So it's, kind of like it's halfway there, right? Like it's not like super important in the network, right? Um, but you can also look so in the case of directed networks, I'm just going to show the code. I'm not even gonna calculate it for something specifically. But for directed networks, you can check the in degree and the out degree. So whether like the degree centrality, if it's like a network that is receiving a lot of edges towards it coming from other nodes, or rather if it's one node that is sending out a lot of edges towards other nodes, right? A different measure is closeness centrality, which considers that the nodes that are important are those that are close to other nodes. So those are like nodes that have a very short distance to what other nodes. So basically the same logic as with degree centrality applies here. Just run this to create the close end. You use it to create close end, and then you run it or in the node that you're interested, right? So in this case, B has a higher closeness centrality than degree centrality. So maybe it's not so maybe B is not that, like 0.44, it doesn't have that many connections by comparison, but it's more central. It has a shorter distance from closeness centrality, right? It has a shorter distance to other nodes. In case you have a non-connected graph, so once again, a graph like this will completely ruin your closest centrality measurement by the traditional way of calculating it. So what you can do is you can normalize it. So you just run this, like extra parameter that says normalize, and then you can actually connect. It controls for the fact that it's separated into two components, right? Another measurement is betweenness centrality, which tells you that nodes that are important um, are those that connect to other nodes based on distance. So the betweenness centrality can be calculated using this to get the between cent. Let's call it like function, or it's not really a function, but you know what I'm saying. Um, um, to calculate that, like I would with the other measures of centrality. So I'm normalizing it, and then I'm using the endpoint false, which is that you can include or exclude the node as an endpoint, right? So it will give you a different measurement. And additionally, this one is supposed to, for a really big network, obviously this has like 10 nodes, but say like you have like millions of nodes, this one is supposed to be computationally more complicated, but you can actually use a sample. Sorry, you can include a parameter at the end, which would be k, that you can actually indicate it to use a sample of all the nodes. And then you can get the betweenness centrality for B, which is 0.02, which is really, really low. So in the case of it being a node that connect other nodes, basically that's not really important, right? Like it's a very relevant node for this measurement. So you can also get the same for edges, so you can realize if an edge is important or not. And then there are two more measurements that I'm gonna show, and then I'm kind of like done with this really basic, just like a general ideas of measurements that you can get up, because I don't want to make like a gigantically long video, and I have more code down. But I think this is like I don't want a video that's like super long. Basically, I just wanted to show these ones because I thought it was interesting, even though I'm not gonna delve into like the logic of how they are calculated. So the first one is PageRank, which apparently was designed by people when they created Google, and it assigns a score of importance to each node, and then in an iterative process, it uses an algorithm to update how important nodes are. So this one is usually better for directed graphs such as this one. And then it takes into account the relationships and like how many edges are going from one graph to the other, and it starts to iteratively redistribute the importance of each node until it leads to it stabilizes after several cases. So what you can do is run this NX PageRank you have to set an alpha parameter. Alpha point 0.8 is, I think, the standard one, and then it will give you the page rank for each of the nodes, right? So then you get, yeah, like the page rank for each one of the nodes from A to E. Um, so this is like an interesting way of doing this, and this is like a way of seeing how the information travels from one node to the next, and how much it's lost. So like things like, I don't know, like these are hyperlinks between web pages, and you are like um, you start in A and you can choose just go to C or B, and then eventually you end in D. This is like an interesting way of calculating this. And then Hobson authorities is very similar, um, but it gives you two scores. So the right, so the authority is like the page that is really relevant or important, but the hubs are, well, in this case nodes. Sorry, the hubs are the nodes that lead you really important um, to really important nodes. So like D has a very high score um, as an authority, but it has 0 as a hub because it doesn't let you to any new pages, right? Whereas A has 0 as an authority because no one reads you to A. So I just wanted to go like really fast over some measurements that I have been um, seeing, and I wanted to give like some basic resources that I kind of like um, got. So I found that there's an annual review of political science and network theory. It's by Michael Ward, Catherine Stovall, and Audrey Sachs. So if it's a way of looking at what kind of research is being done using networks, and how can networks be used for research in political science, especially because I'm getting a little bit into this world. I don't really have that much experience. I remember I took like as an undergrad, there was a methods class that I took that had a section on network theory, but it was very little. But we don't really, honestly, I don't think we get a lot of uh, information on this. So this is a way of getting like some resources into it, like reading an annual review. Um, and of course, it's a different way of thinking about about political science, for example, because you can really have like like this sort of like completely isolated node, and you're controlling from everything else, and there's no endogeneity. It's kind of impossible in a network, right? Um, so other resources is the Data Science from Scratch book, right? That Kularici told us that it was a good book to check for this class. It has actually a chapter on network analysis, um, mostly focusing on centrality measurements. So that one's an interesting to look at even more code and think of ways that it can be used for different things. It has a little bit of very short section further resources, but it's kind of like like if you're even looking for more stuff. And then the final thing is the University of Michigan has a Coursera MOOC on network analysis. This is part of an applied data science certificate. So actually a lot of these I learned, and I looked at the code thanks to this MOOC, which I'm doing. I will probably I'm basically doing like a basic immersion into it, but I'll probably go back to it. But this one has a way more code and uses for network analysis that what I just showed. Um, also because I don't want to be sued by them for using their code and knowledge in a video. Um, but also it has further resources, and so I think this is like some very basic ideas of what are networks made of, and how can we think of